So as we've been talking about like crazy, if we have a magnetic field and we have a particle entering that magnetic field, right, at a certain velocity, it's going to feel a force upwards, right? So charged particles moving through magnetic fields feel a force upwards, right? But what if I have a wire sitting inside of a magnetic field? Okay, so let's say now, here's my wire, right? And there's a current traveling in it, right? I put a current through that wire. What is a current? What is a current made of? It's made of a whole bunch of charged particles, right? We think of it as a stream, this flowing of positive charged particles, right? That means that there should be a force everywhere here on this wire moving inside of a magnetic field, right? It makes sense. If there's a force on any one proton, right, there's going to be a force on all the protons in there, which creates this net force on the whole wire, okay? So if the force before on a single particle was QVB sine theta, we need to convert this equation for a whole current, okay? So instead of one single charge, you have a whole current, right? And instead of one little velocity here, you have a whole length. So we have L here, which is the length of the wire inside the magnetic field, right? And B is still just B, and sine theta is still just sine theta, right? So we can turn the force on one single particle into a force on an entire wire. And this is true of all wires that are moving inside of magnetic fields, where the magnetic field is perpendicular to the current, okay? Or at least makes some angle with the current, theta, okay? So that force, once again, is the current moving through the wire times the length of the whole wire times the magnetic field that the wire is passing through, okay? And one kind of interesting application of this that we'll check out right here is something called a magnetic balance, okay? It's a way to use a magnetic field to actually make something hover, okay? So as this picture suggests here in the magnetic balance, let's take a look. We have a battery, right? And we have a little resistor. It's 5 ohms, okay? And we have over here a bar that is moving through a magnetic field. Okay? So from that bar is hanging some sort of mass m. Okay? And here I have the mass being 2 kilograms. I have the length of this being 1 meter. And this B field here is 3 millitesla. B equals 3 millitesla. Okay, so the question is then, A, what current direction is needed so that the bar is balanced against gravity? Okay, so again, this is right-hand rule, right? We want a force going up, right? So if I want a force going up to balance out gravity going down, so let's draw the free body diagram here just for funsies. We have on this rock, or we have on this this wire, this piece of wire, we have a magnetic force going up that we need to cancel out a weight going down, and that weight is this mass times gravity, right? So in other words, FB minus mg equals 0, or FB equals mg, right? This is what we need in order for this to hover, okay? But remember, FB is really, what is it? Well, this is perpendicular, so this is just going to be 1. Sine theta is just going to be 1. So this is just ILB, right? So in other words, we have ILB equals mg, right? And if I want to find the current needed to make this levitate, to make this float, then that's just going to be I equals mg over lb, right? So this is jumping a little bit ahead because part B wants the magnitude of that. But right now the question is, what direction of current, this way or this way, will give you a magnetic field, a magnetic force that makes this hover, that pulls this up against the force of gravity? Okay? Well, right-hand rule, we want that force to be upwards, right? My magnetic field is pointing into the page, into the board, which means the current must be going in this direction for that to happen. So you would say the current must be going to the right. In other words, the current's going like this through the circuit. Okay? All right. What magnitude must the current be so that the magnetic force on the wire balances with gravity? Okay, well, let's just go ahead and substitute this in. What is our mass? Well, it looks like our mass is 2 kilograms, right? Gravity is 9.8, last time I checked. The length is just 1 meter. That's really easy. And then the B field is 3 millitesla. That's 3 times 10 to the minus 3 Tesla. Correct? All right. If I do that, I get a current of 6,533 amps. Okay. You know, it takes a lot of current in order to make that happen, which makes sense because you're actually balancing a 2 kilogram mass that's like, you know, almost 5 pounds, right? So yeah, you need a pretty big current, but the bottom line is you can do it, and that's pretty cool. All right, last part of this problem. What voltage must the battery have to achieve this current? Okay, what battery must the voltage have? Well, I'm talking about a current, I have a resistor, and I'm looking for a voltage. I know what you're thinking, and you're probably right. V equals IR. This is an Ohm's law problem. So we want to find out what voltage will give a 6,533 amp current when you have a 5 ohm resistor. And so that voltage is 32,665 volts. Lovely. All right. You are getting pretty powerful now. You are now able to master the physics of electricity and magnetism and the force of stuff we did last semester and combine them together into one framework where they're kind of all interrelated. And that's the beautiful thing about physics. Everything in physics ties in and weaves back together. It's a very beautiful, very elegant science, and I hope you get at least a flavor of that. All right? I'll see you in the next video for the Why Do We Care?